In this online lecture, we're going to discuss the fourth and final aspect of NMR, and that simply is peaks can be split due to neighboring/different hydrogens. I want to start out with showing you how to use this rule, and then later on we'll get into why this happens. But let me first start by introducing it to you here. Let's say we have this sample molecule right here. Again, we stick him in the NMR, and therefore he has A-type hydrogens and he has B-type hydrogens, which so far we've learned that if we looked at his spectrum, we should expect to see two peaks, one for the A, the other for the B. However, there was something going on this whole time that we never talked about, and that's basically this. Let's look at that B peak first. Let's say that you were going to look at this spectra really close and you're going to focus on this B peak, and you're going to get a zoomed up view, let's say a 10 times zoomed up view of that B peak. Looking closely, you'll see that it's actually not a single peak. It actually is three peaks that are extremely close together. What we're saying here, and here is some vocab, is that the B peak is actually being split into three peaks. And here's another vocab word here. If that happens, something that's split into three peaks would be called a triplet. The same thing would happen if you looked at the A peak up close. Again, looking at a really zoomed in view here, you would actually see that A is split into actually four peaks. This is called a quartet. And let's pause for a little more vocab here. What we're doing is simply we're looking at the multiplicity of these peaks, which simply means we're looking at how they are actually split up upon close examination. The peaks split due to something called spin-spin coupling. We'll go deeper into this a little bit later. Another term we should know is that the A and B hydrogens are considered coupled hydrogens. And coupled hydrogens have a tendency to split each other's signal, or peak. Now, that's definitely a lot of orgo jargon here. Like I said, we'll get down to details a little bit later, but let's at least learn how to predict the splitting that would be observed given a molecule on his NMR spectrum. So, let's look at the actual split up peaks here for our sample molecule, and again, let's relabel them. Remember, he is the A-type hydrogen, and this would be the B-type hydrogen. We have our quartet A, we have our triplet B. And remember, looking at our molecule in the NMR, these hydrogens are the A hydrogens, and these hydrogens right here are the B hydrogens. What we want to learn first here is that splitting follows what's called an N+1 rule. And here it is. This is just a simple formula, with N equaling the number of neighboring or different hydrogens. So let me show you how to apply this rule. Let's start with the A-type hydrogen. What we want to do is first calculate his N value. And here's how we do it. Notice right here are the A hydrogens. They are directly connected to this carbon right here, which means this carbon over here would be what we can call the neighboring carbon. And that would mean these hydrogens right here are A's neighboring hydrogens. In other words, simply they live next door to him. So it's the B hydrogens that are A's neighbors, and there are a total of 3 B hydrogens. So the number of neighboring or different hydrogens for A is the 3. So if that's his N value, plugging into the simple N+1 formula, 3 plus 1 equals 4. Notice this value that we're getting, 4, matches up to the number of splits for the A signal. He is split into 4 signals. That right there is using the N+1 rule to predict how a signal would be split. Kind of strange, because think about it, when have you ever done anything like this before? This is something very unique to organic chemistry, and I promise you we'll do plenty of examples and you'll get a feel for this, and you'll be able to do a lot of problems on your own very soon. Let's try it with the B hydrogens now. Again, we're going to evaluate them and figure out what is the N value for the B hydrogens. Well, remember, here they are right here. They are directly connected to this carbon right here, which means the neighboring carbon would be this carbon, which means these hydrogens, the A hydrogens, are his neighbors. And how many are there? There happens to be 2 A hydrogens. So the N value for the B hydrogens is 2. And plugging into N plus 1 here, 2 plus 1 is 3. Notice again the value that we're getting here matches the number of split peaks over here. So I want to point out here, it's important, we can look at an actual organic molecule and predict not only how many signals will be in the HNMR, but how the signals should be split up. We're going to see later on that this is extremely valuable information. So for now, just please take my word that this is a valuable skill, and let's look at some examples to try to really get this skill down. So here's our first sample problem right here. Notice how it's worded to give the multiplicity of each kind of hydrogen in the molecule. That's sometimes how questions like this are worded on an orgo test. Or it might say something like, give the splitting of the signals. So let's pull it off here. What you do is start out with the first aspect of NMR, figure out how many types of hydrogens are in your sample. We'll start right here and call these the A-type hydrogens, which would make these right here the B-type hydrogens. Now that we know that, let's start out with the A hydrogens and figure out what their N value is going to be. Again, remember, you focus on the hydrogens here. We notice that he has these hydrogens right here, the B hydrogens, as his neighbors. And how many are there? A total of 2. So the N value for the A hydrogens is 2. Plugging in, N plus 1 in this case, would therefore equal 3. So we should expect to see the signal for the A hydrogens to be split into a triplet. Let's now do the same thing for the B hydrogen here. What is his N value? Well, here they are. These are the B hydrogens. Their neighbors are these hydrogens right here, the A hydrogens. How many are there? There happens to be 2. So B also has an N equals 2 value, which means again, N plus 1 is also going to equal 3 here, which means even the B hydrogens are going to be split up into a triplet. We want to get to a point where we can do this all mentally in our head and very quickly. All it takes is a little practice. So let's look at another sample problem here. What is the multiplicity that we would expect for this molecule? Well, again, let's start out and label our hydrogens. This would be an A-type hydrogen, and remember, so would these guys right here. He would be A, he would be A due to signal averaging. That means these hydrogens right here would be the B-type hydrogens. Let's start out with the A-type hydrogens and figure out the N value. What is the A hydrogen's N value? Well, let's start with 1 right here. And here's the thing, if all these A hydrogens are equivalent, then it doesn't matter which A hydrogens you investigate, you're going to get the same answer. If you don't, it simply means the A hydrogens are not equivalent. So let's just randomly pick these A hydrogens right here and try to figure out the N value. Notice the A hydrogens are directly connected to this carbon right here, and this carbon here has this carbon as its neighbor. And notice that carbon has 0 hydrogens on it, which means the N value for the A hydrogens is 0. We need to know that that's possible. Which follows, if you put it in the N plus 1 rule, 0 plus 1 is just 1, which means we should expect to see the A signal as a singlet. It therefore is not going to be split. We'll see this often in other examples. Now let's investigate the B-type hydrogens. What is their N value? Well, here they are right here, the B hydrogens. Notice they are directly connected to this carbon right here, making this carbon the neighboring carbon. And again, that carbon has no hydrogens on it, so the N value is going to be 0, which therefore, plugging into the formula, 0 plus 1 equals 1, so the B hydrogens would actually appear as a singlet on the HNMR. Let's look at another example here. What's the multiplicity for this molecule? Well, again, let's label our hydrogens. These are the A hydrogens. These would be the B hydrogens, and because of symmetry, these would be A hydrogens as well. So let's start with the A hydrogens and try to figure out their N value. So here they are right here. They are directly connected to this carbon, making this carbon their neighbor, which means the B hydrogens are the neighbor to the A hydrogens. And there happens to be 2 B hydrogens, so the N value for the A hydrogens is 2. Plugging into the formula, 2 plus 1 is 3, so we should expect to see a triplet for the A hydrogen signal. Notice we would get the same result if you investigated these A hydrogens right here. Again, they're connected to this carbon right here directly, making this the neighboring carbon, which means these are his neighboring hydrogens. And again, there are 2 of them, so the N value would equal 2. 2 plus 1 again is 3. You would get the same answer, a triplet. So on an orgo test, we only have to evaluate one of them. However, the B hydrogens are not the same, so we should try to get their N values. So let's look at the molecule here. These are the B hydrogens. They're directly connected to this carbon right here. But notice in this particular case, this carbon technically has 2 neighbors, one on either side, which makes these right here B's neighboring hydrogens. And how many are there? Well, notice 3 on the left, 3 on the right, makes a total of 6 neighboring hydrogens for the B hydrogens. That means the B's N value is 6. So notice in this example, it's possible to have more than one neighbor. And in this particular case, we simply add up the total, which means plugging N into the N plus 1 rule here, 6 plus 1 is 7. And typically when you have that many split peaks, it's usually termed a multiplet, which just simply means a lot of splits. So now we know what to do in cases like this. However, watch what happens here. Let's look at another example. This one's going to be a little bit different. Same instructions, give the multiplicity. And again, let's start somewhere and call these the A-type hydrogens. That would make these the B-type hydrogens. And because this molecule doesn't have symmetry, notice there's an F on the left and a Cl on the right, that would make these C-type hydrogens. Now let's look at the multiplicity here. And let's start with the A-type hydrogens. What is their N value? Well, again, here they are right here. They are directly connected to this carbon, making this carbon right over here the neighboring carbon, and making these B hydrogens his neighboring hydrogens. There happens to be 2 of them, so his N value equals 2. 2 plus 1 is, of course, 3, which means we expect to see A as a triplet. Now let's investigate the B-type hydrogens. What is their N value? Well, notice here they are right here. They are directly connected to this carbon right here. And like we saw in the previous example, this carbon happens to have 2 neighbors, one on either side, which makes these right here the neighboring hydrogens, giving us 2 A hydrogens on the left and 2 C hydrogens on the right. But there's something very important you need to know here, is that when you have a situation like this, the N plus 1 rule fails. Meaning this, if you are a hydrogen that has neighbors on both sides of you, and each neighbor is different, like in this case, one neighbor is an A, the other neighbor is a C, then the N plus 1 rule is not going to predict the correct number of splittings. Later on, I'll show you how to figure out exactly how many splits you might get. But I just want you to know for now, you can't use the N plus 1 rule in this case. All we can say at this point is that whatever the B hydrogen is going to look like on the NMR, it's at least going to be a multiplet. In some sample problems, we'll see that that's enough information that we need. Other times we might need to know exactly how many split peaks we get. So again, just to make sure you got this, if you're a certain type of hydrogen and you have 2 neighbors that are different, don't use the N plus 1 rule. Notice, contrast this with the previous example. Remember, when we looked at this B hydrogen, he had 2 neighbors, but the 2 neighbors are equivalent. Remember, in this case, the N plus 1 rule does work, which in this case gives us an N value equal to 6. So let's go back to our sample problem here. Now we know. Let's just finish it off here and look at the C-type hydrogens. What is their particular N value? Well, again, we start with them. Here they are. They're directly connected to this carbon right here. This carbon has this carbon as a neighbor, which makes the B hydrogens the neighboring hydrogens. There are 2 of them, so the N value for C is 2. 2 plus 1 is 3. We should expect to see a triplet for the C-type hydrogens. Let's look at another example here. Watch what happens in this case. Again, same instructions. What is the splitting? Starting with this molecule here, we'll say that these are the A-type hydrogens. We'll say that because we have a line of symmetry right here, that means these are A-type hydrogens as well. Which means if we try to figure out the N value here for the A-type hydrogens, notice you can start right here and say here they are. They're directly connected to this carbon, making this the neighboring carbon, making these the neighboring hydrogens. And there happens to be 3 of them. But remember, the N+1 rule says that N is the number of neighboring / different hydrogens. Notice these hydrogens in the green box are not different from the A hydrogens. They are actually A hydrogens. So since they're not different, we don't count them, meaning the N value for the A hydrogens in this case is 0. And plugging into the formula N+1, we end up getting a value of 1, which means we should expect to see a singlet for these A hydrogens. Here's another way to think about this point. Always remember that a peak or a signal cannot be split by its equivalent, meaning in this case, A hydrogens are not going to split other A hydrogens. So let's look at another example here. Again, what's the multiplicity for this molecule? Let's start right here and call this an A-type hydrogen, but notice we have a plane of symmetry, so this would also be an A-type hydrogen. And if we try to figure out the N value here, what is the N value for the A hydrogens? Well, remember, no matter which A hydrogen you investigate, he doesn't have any neighboring hydrogens that are different from him, so his N value equals 0, or again, remember, you can't be split by your equivalent, so that means that in the N+1 rule here, we're going to get a value of 1, which means we should expect to see a singlet. So here's another example of not being split by your equivalent. However, look at this example right here. What's the splitting in this case? Well, let's call this the A-type hydrogen, but notice now we don't have symmetry here, so this would be a B-type hydrogen. And let's figure out our N values, and of course let's start with the A hydrogen. Well, here he is right here. Notice he's directly connected to this carbon right here, which makes this carbon his neighboring carbon, which in turn makes this the neighboring hydrogen. You might think this is different from what we've been doing before, but this is the exact same type of analysis that we've been doing this whole time. So the N value for the A hydrogen is 1. He has 1 neighboring B hydrogen. Plugging into the formula here gives us 2, which means we should expect to see the A hydrogen as a doublet on the NMR. Let's analyze B now. What is his N value? Well, again, starting with him right here, he's directly connected to this carbon, which means this is the neighboring carbon, which makes A his neighboring hydrogen. And how many are there? There's just 1. So the N value for the B hydrogen is 1. N+1 in this case equals 2, which means even the B hydrogen will be split as a doublet. Now you know how to handle things like this. Let's look at even another example here. Watch what happens in this case. This is a unique situation, but we need to know how to handle it. Again, let's label our hydrogens. This is an A-type hydrogen. And remember, because our double bond here can't be rotated, that would make this a B-type hydrogen. And going on to figure out the N values for each hydrogen, the N value for the A hydrogen, notice what happens here. This is our A hydrogen. He's directly connected to this carbon right here, which technically means this is the neighboring carbon. But notice this neighboring carbon has no hydrogens on it. But technically, he does have this hydrogen right here, the B hydrogen, as a neighboring hydrogen. Remember, let's look at our N+1 rule again here. Remember, N is the number of neighboring, or we can say, or different hydrogens, which means for this particular case, the N value here is 1. And just to make sure you see this, it's 1 because B is A's neighbor, which means, again, plugging into the equation, n plus 1 equals 2, we should expect to see a doublet. Notice this right here is different from what we've been doing before. Notice both of these hydrogens are connected to this same green carbon right here. And what we want to learn from this example is that it is possible to be split by a hydrogen that's connected to the same carbon. In fact, this is a special type of splitting or coupling, and it's called geminal coupling. We're looking at this example simply to know that we need to do this if we're confronted with something like this. So, to make sure you got it here, let's look at the B-type hydrogen now. Again, what is his N value? Well, we start by looking at him right here, and the only neighboring hydrogen he has in his vicinity is this A hydrogen here, so his N value is 1. Plugging into the formula gives us N plus 1 equals 2, so we should expect to see the B hydrogen split into a doublet. Let's look at another example here. Sample problem 9. What is the splitting observed in this molecule? Well, remember the first thing we should do is fill in all the hydrogens that would be present. Here they are. And let's start somewhere and call these the A-type hydrogens. That would make these the B-type hydrogens. And remember, since benzene rings are symmetrical, these would be the C-type hydrogens, making these the D-type. And this last one right here would be an E-type hydrogen. And let's start with the A hydrogens and let's figure out what their N value would be. Well, here they are right here. A's neighboring hydrogens would be the B hydrogens right here, and there happens to be 2 of them, so his N value equals 2. 2 plus 1 is 3. We should expect to see a triplet for the A. Now let's investigate the B-type hydrogens. What are their N values? Again, let's look at them right here. The only neighbors he has are really these A hydrogens right here. Notice the carbon that the B hydrogens are on is also directly connected to the carbon below it in the benzene ring. But notice that carbon in the benzene ring does not have hydrogens connected to it. So B only has A hydrogens as its neighbors. There happens to be 3 of them, so the N value for B is 3. Plugging into the formula, 3 plus 1 is 4. We should expect to see a quartet. Now let's investigate the C-type hydrogen. And remember, we could look at either one, it doesn't matter. We're going to get the same answer. Let's look at this hydrogen right here on the left. Notice his only neighbor is this D hydrogen right here. Therefore, his N value equals 1. N plus 1 in this case equals 2. So we should theoretically see a doublet for the C-type hydrogen. Now let's investigate the D-type hydrogens, and we'll start with this guy right here on the left. Notice he has 2 neighbors. He has the C hydrogen as one of his neighbors, and he has the E hydrogen as the other neighbor. And remember, if you have 2 neighbors and they're not equivalent, then the N plus 1 rule will fail, so we know not to use it here. We're just going to say that D is going to be some kind of multiplet. This brings us to the final hydrogen here, the E hydrogen. What is his N value? Well, notice here he is. He technically has 2 neighbors. He's got the D here on the right, and he's got the other D here on the left. But in this case, remember, his 2 neighbors are equivalent, so the N plus 1 rule doesn't fail in this case. And since there's 2 D hydrogens, his N value is 2. 2 plus 1 is 3. Which means theoretically we should expect to see a triplet. Now, what I want to emphasize here, though, just as a side note, is that all we're doing here is all theory. However, I do want to let you know some of the reality here for this particular example. And notice here, it's the C, D, and E hydrogens that are connected to the benzene ring. What I want to show you is how they would actually appear on the NMR. We would see the C being a doublet, the D being a multiplet, and the E being a triplet. That's all still true. But let's look at the actual spectrum. This is what you would actually see here. This would be the A-type hydrogen, which remember we predicted would be a triplet. This would be the B-type hydrogen, which we predicted to be a quartet. But the C, D, and E hydrogens would be right here. What we're looking at is all of them are actually bunched up together. And they're bunched up together so tightly that we can't distinguish their actual splitting for each one. What we end up seeing is all of them collected roughly near 6.5 to 8 ppms. Later on, we're going to see that sometimes this is enough information to help us predict product. We don't have to actually resolve each individual hydrogen. We'll talk more about this later. However, there's something every smart orgo student should know about NMR, and that's in cases like this. Look at this molecule. It's a little bit different from the one we were looking at before. This one now has a methyl at the bottom here. Let's quickly investigate him. Let's call these the A-type hydrogens. These would be B. These would be the C-type hydrogens. These would be D-type hydrogens, and the hydrogens on the methyl would be the E-type hydrogens. If you were to look at his actual HNMR, you would actually see peaks that look like this. And take my word for it right now, these would be the hydrogens due to the C and D hydrogens. Again, notice they're directly connected to a benzene ring, and they peak at around 6.5 to 8 ppms. But in this specific example, notice how these peaks look. They're symmetrical. It kind of looks like two doublets next to each other. Anytime you see this on an HNMR, it is extremely strong evidence for what's called a para-substituted benzene ring. And what does that mean? It means that the benzene ring has substituents that are para to each other. Look at the molecule on the left. Notice the bonds in these green shaded boxes. What you're seeing here is, and using the vocab, is that the top ethyl substituent is para to the bottom methyl substituent. Or in other words, they're across from each other on the benzene ring. This kind of para substitution is very popular in organic molecules. So you might see this type of splitting a lot. This is very valuable information on an orgo exam. It means that if we see peaks that look like this between 6.5 and 8, we're going to know right away that not only does our molecule have a benzene ring in it, but it's also para-substituted. But you'll see, when we get to structure determination, we'll see even more how this comes into play. Now, while we have this example in front of us, let's just finish it off just in case. These would be the A-type hydrogens right here. Notice they do have the B hydrogens as neighbors. There's 2 of them. 2 plus 1 is 3, so the A would be a triplet. That makes this signal right here the signal for the E-type hydrogens, and notice here they are. The neighboring carbon for them would be this carbon here. He has no hydrogens on him, so N equals 0 for the E hydrogens, which means 0 plus 1 is 1. We should expect to see a singlet. And lastly, this should be the signal for the B-type hydrogens. Notice these B hydrogens right here only have A as their neighboring hydrogens, and there happens to be 3 of them. 3 plus 1 is 4, so that's why B is appearing as a quartet.